I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on current and resistance, the tools that measure those, the resistivity, Ohm's law, and electrical power. In this video, we're going to talk about current and resistance, the measuring tools that measure those, resistivity, Ohm's law, and electrical power. So let's start with electric current. So we're going to start with our capacitor, parallel plate capacitor. We're going to hook a battery up to that capacitor, and we know that the charge is going to move off of the positive plate and through the battery to the negative plate. And the current is the rate of the charge that is flowing through the wires of a circuit. This is measured looking at a cross-sectional area, so any cross-sectional area. So let's look at a spot right here on the negative side. And what happens is we have charge that is moving through that cross-sectional area. The rate at which the charge is going through there, that's called the current. So current is the change in charge passing through that spot divided by the time. So the rate at which charge flows through the circuit. For a long time, it was thought that the positive charge is what flowed through the circuit, but we now know that it's the negative charge. So we look at the direction of the positive charge that flows in the circuit, and this is known as the conventional current. Now looking at the equation for current, I, that represents the value of the current, and that's measured in amperes, or abbreviated amps, or just a capital A. Delta Q is the amount of charge that flows through that cross-sectional area of the circuit, measured in coulombs. And delta T is just the amount of time that elapses to allow the current to flow through. Now, an ampere or an amp is the SI unit for current. And the value that it's measured in, if we look at current, we know that current is measured in amperes. Delta Q is a coulomb, and delta T is time or seconds. So an ampere is a coulomb per second. So that's the breakdown for an ampere. Now, what causes the electric current? So we have a simple circuit where we have a battery, a couple wires hooked up to that battery, and we have a light bulb. Now, when we hook those wires up to the light bulb comes on. Now, what's going on that causes that light bulb to come on? So when the wires are connected, there's an electric field that's created in the wires that we know points from positive to negative, and that's because of the potential difference across the battery. So that electric field points from positive to negative, and we know that a positive charge is going to move from that positive high potential through the wires, through the light bulb, to the negative side of the battery to decrease the potential. And that positive charge flowing is the direction of conventional current. Now, this is the cause of a positive charge to move through the electric field and wire. Now, the electric potential decreases and reaches zero at the negative terminal of the battery, and delta V has the largest change that's across the light bulb. So a cell is what provides the electric potential in a circuit, and what it does, it converts chemical energy into electric energy, and it's a single unit device, so it's represented by a long line and a short line. Now, a battery consists of multiple cells, so you might see multiple long and short lines to represent a battery, or it might just be a single long and short line to represent the battery. But what the battery does, it acts as a charge escalator. It's working on the charge to move it in the opposite direction of the field, and it increases the potential of each of the charges. So we see the battery just lifts the positive charge from the negative end of the battery to the positive, moving it in the opposite direction due to that chemical reaction that occurs inside the cell. So what a cell does is it produces a voltage called an EMF. The symbol is a script E, not a Greek letter. Now, a side note that EMF used to stand for electromotive force, but it's not actually a force. So the EMF is still used to describe what a cell provides, but it doesn't stand for anything anymore. So the EMF depends on the chemistry of the cell. The terminal voltage, or the actual voltage, what's read across the battery, is equal to the EMF in a perfect cell. Now, most batteries you buy in the store are 1.5 volts, so as that battery starts to die, the voltage, or the terminal voltage, is not reading 1.5 volts because it's starting to die. The chemical reaction is being exhausted at that point. Now, the terminal voltage is less than or equal to the EMF of the cell. It can't exceed the EMF. That's the maximum electric potential that can be provided by the cell, is the EMF, but it can be less than that if there's internal resistance. So So we're going to talk about measuring current and voltage. We're going to look at our simple circuit with a battery and a light bulb. So we're going to start by measuring voltage, and voltage is measured with a voltmeter. Now a voltmeter has to be set up in parallel with the bulb that is being read for potential because it has a very high resistance to current flow, and basically it's equivalent to zero, the current, so it's actually as if it's not even set up in the circuit. So we'd hook it up like this to measure the potential. Notice the value of the potential is negative because the potential is dropping as it goes from positive to negative, remember. Now this tool is called a multimeter, and a multimeter measures three things: measures the potential, the current, and the resistance of elements within a circuit. So next we're going to talk about measuring current. And current is, we use an ammeter, so the multimeter would be set up as an ammeter. And we measure that in series with the bulb because we want to know how much current's flowing through the bulb, so it has to be in series with the bulb. Now, an ammeter has a very low resistance, so basically there's no potential drop through the ammeter. So what we're going to do is we're going to disconnect our light bulb, and then we're going to place our ammeter in series with that, and we can see that the current has a value of 0.11 amps. So that's the current that is flowing not only through the light bulb, but also through the battery because everything is set up in series. Now the current, remember this is conventional current, is going to come from the positive side and through to the negative side, and there's no current that's going to flow through the voltmeter. So drawing a schematic diagram, we know batteries are a long line and a short line, the long side representing the positive end of the battery. And a light bulb is going to just be a circle with a squiggly line inside to represent the bulb. And an ammeter, we're going to represent with a circle with an A in it, so we know that it's an ammeter, and that's set up in series. And a voltmeter, we're going to set up hooked up in parallel with that resistor. It's just going to be a circle with a V in it, so we know that it's a voltmeter. Now let's talk about resistance. So in a circuit, if the current is directly proportional to the potential, so if we added multiple batteries, the current increases as the voltage increases, the ratio of delta V to I is known as the resistance. Materials where this ratio holds true are known as ohmic materials or ohmic resistors. And that's where R is going to equal delta V divided by I. And this is known as Ohm's law. So R, that stands for the resistance of an ohmic material, and that's measured in ohms, which is the Greek letter omega. Delta V is the potential difference across the resistor, that's measured in volts, and I is the current flowing through the resistor, and that's measured in amperes or amps or capital A. So an ohm is defined as a volt per amp using Ohm's law equation. Now the way you're going to see it written on your formula sheet is I equals delta V over R, but we're going to rearrange that equation even more, and we're just going to say delta V equals I times R, and this is what we're going to use most frequently in electrical circuits when we get a little bit more complicated with those circuit diagrams. Let's talk about ohmic and non-ohmic materials. So we know that an ohmic material has a direct relationship with current and potential, which means that that would give us, in a graph, would give us a straight line graph where the slope would represent the resistance. And this would be a graph of an ohmic resistor of taking measurements. Now, if it's a non-ohmic material, that means we're not going to have a direct relationship, and that means we'll have some sort of a curve. Now, most non-ohmic materials actually increase in resistance, which means that it'd be proportional to the potential squared. So the increase in resistance is shown through that curve. So if we have a curve, that's a non-ohmic material. A straight line would give us an ohmic material. Now, resistance and resistivity are not the same thing. Resistance is a measure of how resistive a substance is to the flow of electric charge. So if we look at a section of a wire, and it looks like zoomed in, it's a cylinder, we're going to look at the proportionalities for resistance. So the longer a resistor is, that means the more distance the current has to travel, so it's going to be a direct relationship to resistance. The length increases the resistance. If we increase the cross-sectional area, however, current can flow through a larger area much easier. So that means that resistance and area are an inverse relationship. Now we know that we can take any proportionality and make it an equality by simply multiplying by a constant. So we're going to multiply by the Greek letter rho, and we'll talk about what that means in the next slide. So R, that's the resistance measured in ohms. L is the length of the resistor, that's measured in meters. A is the cross-sectional area measured in meters squared. Now rho is called the resistivity constant of a material, and that's measured in ohm meters. And each substance has its own specific value of a resistivity constant. So that is based on the material. So aluminum, glass, copper, all have their own resistivity constant. So let's look at a visual representation of resistivity at the molecular level. So we have two different wires that we have set up here, two different substances. So if we look at the molecular level, it might be nice, neat, and organized with a structure of molecules so that current can flow through that easily. So this would be a low resistivity. So this might be a substance like copper. Now, if we look at it, the other substance, maybe it's a lot more complicated, a lot more complex, which means that current's not going to flow through it very easily. Well, this would be a high resistivity. So this might be a substance like glass that has a high resistivity. And remember, resistivity has to do with the substance. It's a constant no matter the substance. Copper will always have the same resistivity, and so will glass for its resistivity. So measuring resistance. So in a schematic diagram, this is what a resistor would look like, a zigzag line. So we're going to measure resistance using an ohm meter. So this is an ohmic resistor that we have here. And you cannot have the resistor set up in a circuit. You're just going to measure the resistance before you set it up in a circuit. Take our multimeter and set the wires on either side of the resistor to give us a reading of 1.000 kiloohms, or 1,000 ohms would be the resistance of this ohmic resistor. Now let's look at resistors in a circuit and schematic diagrams of a simple circuit. So we know a battery is a long line and a short line. The wires are straight lines and right angles. The resistors are going to be zigzag lines set up within that circuit. So an ammeter is just a circle with an A in it set up in series. And a voltmeter is set up in parallel along a resistor or a battery to measure the potential difference across that resistor or battery. We're going to transition and talk about electric energy and power. So we're going to look at our simple circuit diagram of a battery with the positive side being the long line. And we'll set up some points in our circuit, points A, B, C, and D. So what we're going to do is we're going to look at a positive charge as it flows through the battery. And when it makes one complete circle, we know that the change in potential is zero when we end and start in the same spot. So if we start at the negative end of the battery, the potential energy through the battery is going to increase by delta Q times delta V as the charge moves from point A to point B. Now the chemical energy of the battery is going to decrease by the same amount. So that chemical energy is changing into potential energy, electric potential energy, for the individual charges as it pass through the battery. Now, as the charge moves through the resistor, collisions between the charge and the atoms of the resistor convert this potential energy into thermal energy. So the resistor gets hot. And the wires have a low resistance, so there's no energy that's lost from point B to C or from D to A. So as that resistor gets hot, then it starts to glow if it's a light bulb. So as the charge goes completely around the circuit, and the net result is that chemical energy from the battery is converted to thermal energy to increase the temperature of a resistor. And as we said, the light bulb then starts to get hot, and that wire in the light bulb glows when it gets hot, and that's how a light bulb works. Now, it also takes a period of time for that charge to flow through there. So as that energy is converted from electric potential energy to thermal energy, the rate at which energy is being lost from the charge is called electrical power. So power is the change in electric potential energy per time. Electric potential energy is delta Q times delta V, and we know that delta Q divided by delta T, well, that is our definition of current. So power is equal to the current times the change in potential, And both of those are easily measured with a multimeter in an electrical circuit. Using Ohm's law, Ohm's law is I equals delta V over R, so we can actually derive other power equations from the original one. So power is equal to delta V squared over R. If we look at delta V equals I times R and substitute that in, power is going to equal I squared times R. So these are three different power equations based on what you know of given values or measured values. So power is capital P, that's the electrical power of a resistor. That's measured in watts, which is a joule per second. Power is also the measure of brightness. So the brightness has to do with the amount of current. So lesser current means a lesser brightness, or a lesser potential drop also means a lesser brightness. So when you're asked to discuss brightness of a bulb, you need to talk about current, change in potential, or both, and what happens to each of those values. I is the current flowing through the circuit, that's measured in amps. Delta V, that's the potential drop across the resistor, measured in volts. And R is the resistance of the ohmic material, and that is measured in ohms. So let's recap all these equations for our current and resistance. So the current is the rate of charge flow, which is I equals delta Q over delta T. A battery acts as a charge escalator, and it increases the potential from a positive charge going from the negative side of the battery to the positive side to then be released into the circuit to allow it to drop potential through resistors. Ohm's law relates current, potential, and resistance in a closed circuit. I is equal to delta V over R. Resistance is related to resistivity, the length and the area of a resistor. R is equal to rho L divided by A. And electrical power is the rate at which electrical energy is converted to thermal energy in a resistor. And it's also the measure of a brightness of a bulb. Power is equal to I times delta V, or delta V squared divided by R, or I squared times R. So this is an introduction to current and resistance and electrical power. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.